welcome to this seminar. So I would like to start by just mentioning a few other names, because this work is really based on some collaborative work with Eduardo Grande and Daniel Arachni, both from the Delft University, where I'm currently at, and then also Charles Tinney and Mark Hamilton from the University of Tech, who I collaborated with on the work. Which is, I'm in the aerospace engineering discipline, and actually when we study acoustic footprints of aerospace systems, for instance, propulsive systems such as rotors or jets, typically we look at metrics like the sound intensity in dB or spectra of the sound. But these are just based on time averaging or ensemble averaging, and they exclude any temporal variations in the noise. Now, this talk is really to highlight a few examples of why such temporal variations of the noise are important to include in the acoustic analyses. And I do that by focusing more or less 20 minutes on rotor noise, and then in particularly the modulation of broadband noise. And then in the second part of the talk on jet noise, where we focus on high intensity features of the noise that can be very pronounced in the time series and also for hearing them, but you do not observe those in, for instance, again, the spectra of the noise at all. So focusing the first part of the talk on the rotor noise. Nowadays, a lot of the aerospace vehicles being designed in the class of what we call urban air mobility or advanced air mobility vehicles have rotors or a multitude of rotors. And still the certification procedures fall short in assessing temporal variations, because if you look at the regulations in this policy here, then they are primarily based on the A-weighted sound exposure level or the effective perceived noise level, and none of those preserve certain characteristics that you may see in the time series of the noise. Also, most of the scientific studies, if you look at the literature, about 90 or more than 90% focuses on the spectra or overall sound pressure level. And so it's relatively a neglected topic of research. While we actually know that the time varying properties of the noise are highly relevant for the human perception. So when you listen to the acoustics, and also the annoyance, so how annoying is perceived if a helicopter flies over, for instance. So it's very important for the public acceptance of these new type of aerospace systems that are envisioned to operate in environments much closer to densely populated areas. Now, one of the most maybe well-known features to you of time-varying noise is actually what I would call here modulation of rotor noise, where the modulation time scale is on the order of the blade passage frequency. So you hear that actually on any rotor system. So for a wind turbine, if you're close to it, you hear this whoosh sound on the order of about a 1 Hertz time scale, which is a typical blade passage frequency there. For helicopters, you hear it more on the order of 20 Hertz, and for drones, it can go up to 2 orders of magnitude higher. So it's actually the higher frequency noise that's modulated in intensity by the time scale of the blade passage frequency. Now, the blade passage frequency tone itself is actually created by basically displacement of air by the rotor. So it's called thickness noise, or also loading noise if you actually produce thrust or lift with the rotor. But there are also other noise sources of typical rotor noise, which I do not review extensively in this talk. But there are, for instance, from the blades cutting through vortices from preceding blades. What we focus on in this talk is more the modulation of the higher frequency noise, which is not really well described as a certain source mechanism responsible for it. So first we wanted to characterize it. And the way I illustrate that here is actually with an example. So this is from a measurement of actual rotorcraft noise. And on the top here, we have a spectrum, conventional spectrum. So you see the blade passage frequency and then harmonics. And on the bottom, we see the time series of that noise. And then what we can do is just in the spectral space, we apply a narrowband filter around the BPF. So this in time results almost in a harmonic wave. And then if we just focus on a high frequency or bandpass filter, you can visualize this high intensity noise. And if I draw some sort of envelope of the noise here, the high frequency noise is of a relatively constant amplitude over time. But what you can actually do is you can modulate the higher frequency noise part, which is shown on this slide here, where the envelope of this modulation is kind of the blade passage frequency. Now, importantly, if you modulate this, this noise in time, you actually do not see that as a change in the frequency spectrum, because that's a second order metric and therefore is insensitive to the modulation. So therefore, this time series sounds completely different and you perceive it as more annoying typically when it's modulated, but it does not show up in the spectrum. And therefore, we wanted to investigate this further using order metrics. So the work based on this is really to quantify this, what we call blade passage frequency modulation in the acoustic field. And we wanted to develop a relatively simple method that's just applicable to a single time series, because those data are typically available from microphone measurement. And then also look at the spatial organization of this sound, and also depending on aerodynamic features and loading, because I'm in aeroacoustics, also study the aerodynamic that's responsible for certain noise features. And now this objective actually aligns very well with, in the wider community, we say as there's a need to define measurement methods to support noise regulations for these upcoming vehicles, and also to develop low noise approach and takeoff procedures. So then these new type of metrics would come in very handy. So how do we study this in Delft, the rotor noise? We have this anechoic wind tunnel facility, which is quite a large facility. It spans 3 floors of a building. The air is being pumped down through a shaft here, and then it goes up through a bell nozzle. So it's actually a wind tunnel, vertical wind tunnel, and then there's a stream of air coming out of the floor of this test section, which is an anechoic test section, and then it returns. So it's a return wind tunnel. Now, and in this stream of air, we place a rotor, so we can do both hovering conditions with the wind tunnel off, but also we can simulate forward flight conditions of rotors. Now, the rotor studies itself are based on, in this case, just a 2-bladed propeller. It's a 30 centimeter diameter blade, producing about 22 newtons of thrust. And we do this in both hovering scenarios. So that's actually an advance ratio J, where the free stream incoming velocity is 0, but also at increased, what we call advance ratios, to have different flight regimes of essentially a forward flight propulsion system. Now, the acoustic measurements we recorded with this boom of microphones here on this highlighted part. And we use 40 microphones, and we actually traverse it from the position closest to the rotor, which is suspended here, up to the far field. So what we actually end up having is we have time series at all of these dotted positions. And we also have it synchronized with the rotor position. So if you make a phase average of the acoustics, you get like a movie as such, where you have the rotor now oriented here. You see half the rotor. In this case, the rotor is giving thrust downward. And you see the blade passage frequency in this acoustic field, which spans about 10 rotor diameters to the far field. And you see also these finer scale ripples, which are actually harmonics of the blade passage frequency. Now, as I said, I'm also in aerodynamics. So we also perform typically in these kind of studies flow-based measurements, which we do using PIV, where we seed the flow with particles and we illuminate them with a laser and take images to get velocity fields. And here you see, for instance, from a rotor, actually the vertical velocity, which is high below the rotor, it's almost zero in the free stream here, and you see these helical actually rotations of fluid, which is basically the helical vortex from the rotor tip spiraling downwards. So we use these flow-based measurements to actually say also something about the source of the acoustics. Now, what can we get from these data? So if I would plot purely the amplitude here in dB of the blade passage frequency tone, we see that it is more like a dipole sound here on the right as an arc. And it propagates about 20 degrees below the rotor plane, where the most intense direction is, because this rotor is actually producing thrust. So therefore it is oriented downwards. And this is just the blade passage frequency tone, but I can also look at, of course, all kind of other frequencies. And if I just high pass all the signals at 5 times the blade passage frequency, I get this quadruple sound source, which is characteristics more for the trailing edge or the broadband noise. Now you also see that these are basically all the points are collapsing on a nice curve, which means that for these frequencies, I was in the acoustic far field because I scaled them with the distance 1/r from the rotor up. So you can also see that all the measurements were in the acoustic far field. Now, what we actually don't get from these kind of measurements is, again, this modulation. So on this slide, I just review quickly what we use to quantify this modulation of the higher frequency noise over time. This is a raw acoustic time series again, and we use 2 approaches. So the first one is shown on the top here, where we use a bispectral analysis. So it essentially tells you if you have 2 frequencies in your signal, so on this axis here, frequency 1, and here, frequency 2, then you can get triadic, like scale interactions, so where it is consistent with a frequency f1 plus f2, so a summation or a difference. And that is, for instance, shown here by this red ridge. So this shows that if I take a frequency in my time series of about, in this case, 200 hertz, then this frequency is actually coupled to all the other frequencies in my noise signal. Now, this frequency happens to be the blade passage frequency here, and the fact that it's coupled to a lot of the other broadband, basically, frequencies means that there's a modulation going on. So as one of the quantities, we use essentially the average amplitude here in this boxed region as a metric for how strong the modulation is. Now, maybe a more intuitive way is the one on the bottom. That's also why we included it. And that's actually, I'm just separating the time series into a pure time series of the blade passage frequency, which is on the top, the red line, almost looks like a harmonic wave. And then on the bottom, this is actually an envelope to the higher frequency noise created with a Hilbert transform. Then if you correlate the blade passage frequency with the envelope of the higher frequency noise, that also tells you something about the strength of the modulation. Now, you can do that for every point in our acoustic measurement domain, which is shown here. Now, again, the rotor is placed here, producing thrust downward. And here from about 2 rotor diameters to 10, we see everywhere in our acoustic field what these 2 metrics give us. So first of all, they give us the same trend, which is very reassuring that it's quite a robust metric, and we can either use either one of them. And we also see that, at least for this advance ratio, so this is a hovering condition for the rotor without any incoming velocity, we see that the strongest modulation of the higher frequency noise is again oriented at about 20 degrees below the rotor disc. Now, if you ensemble average your time series, you can also see that for the higher frequency noise, like somewhere here, where the metric indicates a high modulation, you can actually see that over 2 blade passages, so a full rotor revolution, you see an increase in the gray signal amplitude, which is the high frequency noise, then a decrease and an increase. So you would really hear this as a modulation. While if you're above the rotor plane, you see that it's more flat, so it's more constant amplitude noise. Now, we have this as a function of actually the advance ratio. I'm not going into a lot of detail there, but this is related to different source mechanisms, and I'll have a little bit of depth on that on the next slide. I can see if I actually can play one of the noise signals. So here at a location, so below the rotor plane where this modulation is most strong, you hear noise that sounds like this. And then above the rotor plane, so where this metric is also relatively low, it's more constant amplitude. And so these time series, they were relatively low frequency because here I scaled the noise from our laboratory scale to actually a full-scale helicopter scenario. So that's why it sounds more or less like a helicopter flyover. I just have one or two slides on the source mechanism. So what we actually see is that the strength of this modulation at about this 20 degree below the rotor plane is quite dependent on the advance ratio. So basically the operating conditions of the rotor itself. We went into the aerodynamic features associated with these different operating conditions. And what we saw for these relatively low Reynolds number propellers is that at hovering conditions, we actually have a laminar separation bubble, which is a small separation of the flow on the suction side of the blade. And this then reattaches. And when it reattaches, downstream, you have a shedding, so small vortices from the shear layer of that separation bubble. And they pass the trailing edge, and this creates a lot of this broadband trailing edge noise. Now, because this is a relatively low Reynolds number propeller, the separation bubble is relatively sensitive to the angle of attack. And depending on whether you are in a fast forward flight regime or slow forward flight regime, this separation bubble changes in size. And what we saw is that, for instance, for J0.6, the separation bubble doesn't even retach anymore, so it's fully separated flow above the blade. Here it was relatively small separation bubble, but then in these two intermediate J values, the separation bubble reattaches. Now these two scenarios in the middle actually have the largest modulation that you can hear. And we speculate at the moment, we're still doing measurements on this, that this is because here we have a very clear case of these vortices from the separation bubble passing over the trailing edge of the blade, while for this case that is not present. And for the case of J is 0, actually the dominant noise is from blade vortex interaction, because the blade cuts through the tip vortex of the preceding blade. So there you have a constant blade vortex interaction noise, which really dominates everything. Now, at the moment with the PIV measurements, we actually try to explain this quantitatively and verify this hypothesis. Okay, that finishes the first part of the talk on the rotor noise and how we study modulation of higher frequency noise in our experimental aeroacoustics lab. And now I wanted to switch to jet noise. It's another topic that we investigated some time in, and specifically high intensity jet noise, so produced by supersonic jets. And I will also highlight there the importance of actually looking at the time series and analyzing the time series besides just the conventional spectral analysis. So very quick introduction into high intensity jet noise and why it is still relevant. So even though on this bottom right graph, we see that basically this is the average noise of an engine relative to what we call a stage 3 engine, which was developed in the late 1970s, we see that the noise from the aircraft engines goes down. Still, supersonic high-intensity jet noise is very significant, because in the case of supersonic aircraft, which are the ones here on the top, and also the Joint Strike Fighter, one of the newer developed ones, all remain at almost the same source amplitude, simply because you need the exit velocity of the jet to be higher than your flight velocity, and the exit Mach number dictates often the acoustic power. Now, although at the conventional airliners, you could get away with higher bypass ratio engines, which is the primary cause actually for this line to go down over time. So as I just mentioned, the acoustic power basically scales as the Mach number to the 8 of the exit velocity of the jet. And because this remains high for supersonic airplanes under development and fighter jets, this high intensity jet noise remains a very relevant topic. Now, how does typical sound signature from supersonic jet noise looks like? What we see here on the left is actually a jet exiting at 0, and it exhausts to the right. And then these contour lines are the overall sound pressure level. And what you see is this very pronounced directivity, in this case at about 45 degrees, where it is most intense. So actually, if you're closer to the jet in this region, you are at a location with a lower sound intensity. And the reason for this specific very sharp lobe in peak intensity is because there are turbulent eddies in the jet that convect at supersonic Mach numbers, and these generate Mach waves, kind of similar as a shock wave of bullets traveling at supersonic speeds. So that angle is very well defined by the convection velocity of the structures in the jet. And we also see that because we have larger and larger structures in the jet further downstream, actually the lower frequency noise emanates from regions further away from the jet axis, while higher frequency noise, which you actually see in this video, we sweep over frequency. The higher frequency noise emanates from locations closer to the jet on average. So supersonic jet noise in that regard is can be modeled in quite an elegant manner using what we call wave packets. So you can actually model little, let's say, harmonic oscillations in the pressure intensity in the near field of the jet, and you can let them convect with a supersonic phase velocity, and it creates these acoustic waves in the far field. And that catches a lot of these, at least statistically, features of the supersonic jet noise. So people develop aircraft noise prediction models based on this. But again, these are only taking into account the noise intensity of the acoustics that you perceive on the ground, but not really any of the temporal characteristics of the sound. So just as for the rotorcraft, what you typically predict is an effective perceived noise level or some sort of weighted metric with the number of aircraft operations over time. Now, while actually Fox-Williams early on in the 1970s already, from just purely looking at the acoustic time series from, in this case, the Concorde, so that had a supersonic exit velocity for the engine, he observed that if you look at the acoustic pressure as a function of time, you see these very sharp rises, so very sharp compressions, followed by a more gradual expansion. And he named that crackle component. So they sort of what they call sawtooth-like structures in the waveform. And they have been observed for full-scale aircraft. So on the left in the paper by Fox-Williams in 1970s. But then also they have been reproduced in many of the laboratory scale jet noise studies, also in the one that we did here on a Mach 3 jet. In an anechoic facility, if you place a microphone in the far field, you observe these shock structures when you look at the acoustic waveform. So we wanted to investigate further if we can actually relatively easy predict how significant these structures are in your waveform. Because if you listen to a waveform that actually includes these kind of features versus one that doesn't, it actually sounds distinctly different. So it's an important feature to consider when you consider annoyance of jet noise. Now, there have also been various source mechanisms proposed for these specific shock-like structures. It's still a topic of research at the moment. Some say that it has to do with supersonic air pockets that kind of cause a convective wave pileup in the source of the jet. So here you see basically a shear layer developing. You have vertical motion, and that piles up and drives this pressure wave to the far field. Some say that it may have to do with micro explosions of cold air that is being entrained by a hot jet flow, so that it has to do with the temperature ratio of the jet. And some also see that Mach waves, because they emanate from these different regions in a very elongated jet noise source, that they can actually coalesce. So then if you propagate from the near field here to the far field, it kind of causes this steepening in the waveform when two waves coalesce, and this can cause this sawtooth-like feature. Now, aside from these three source mechanisms that people have formed based on some observations, we also know that if you go to very intense noise, you can also get waveform distortion because of nonlinear mechanisms. And that is really a cumulative effect that adds up with outward propagation distance. So it's kind of a different source mechanism. It's not created at the jet noise source, but it's created with travel distance. So a little bit on that aspect, in case you're not familiar with the nonlinear acoustic distortion. You can either have, for a relatively low amplitude wave, a linear propagation. So if you start out with a purely harmonic wave, then if you go to the far field, and I presented here in a retarded time frame, then only the intensity decreases and the waveform remains unaltered. But if you go to nonlinear propagation, where you actually, the sound speed at the top of the waveform is slightly higher because you have a compression and an increase in temperature, you can actually have the distortion of the waveform. So the waveforms actually steepen from the sinusoidal wave into an N wave structure. And the rule of thumb that people use, since Crichton studied this very extensively in the 1980s, is that it's for more or less spherical waves that are in the excess of 160 dB at the source. And this is often the case for these supersonic jets. Now, how does this show up in the time wave form? So as I said, you see from actually a relatively undistorted waveform here, if you propagate this into a, in this case, it was a plane wave tube experiment to distances further downstream, you see that two phenomena actually happen. First, you have a wave steepening, so where you see the occurrence of these very sharp compressions. And then you also have a merging of the waves. So you get less and less waves the further you go downstream because they coalesce. So if you look at a spectrum, close to the source, it may look like this broadband spectrum at 1 feet downstream of the source. Then if you propagate this with high enough intensity in a plane tube, then you get this increase in high frequency, which is basically the signature of the very sharp compressions. And at the same time, you also get an increase in the low frequency because you get less and less zero crossings by the merging of these shocks. Now, this occurs at the same time as, of course, acoustic absorption, which actually tries to counteract this nonlinear steepening effect. So it's really two competing effects that play when you have a high intensity waveform propagating to the far field. Now, what people have done in jet noise, now knowing that you can see these changes in the spectrum, have of course tried to observe this also in the far field spectra of jet noise. But there is actually a few reasons why it is very complicated or hard to see any changes in the acoustic spectrum. Because first of all, you need to look at the change in the spectrum between 2 points, because it's a cumulative effect. So let's say you take a point here in the acoustic far field and one here, and if you compare the spectra with each other, then the difference may not purely be from the nonlinear effect that plays a role, but also because the noise is not a point source, so you actually do have, even in the far field, still different acoustic signatures depending on which propagation path you are essentially using from the cylindrical jet noise source. So people have observed small differences, but it's very hard to ascribe them to nonlinear effects. So people then came up with different kind of metrics. For instance, if you take the waveform and you look at the derivative of the waveform and the asymmetry in that, so basically the skewness, then an N wave has a very high skewness in the that metric. So in every point in your acoustic domain, you can compute the skewness and make a contour map of that. So in a laboratory scale jet, that looks as follows. So here upstream or at sideline angles, the skewness is very low, which suggests that there are no shocks in your acoustic waveform, because there the sound intensity is actually quite low. And then along this direction where you have the peak intensity of the noise, you also see that this skewness term is most pronounced. However, if you look at full-scale data from a full-scale jet, people have observed a similar trend, namely that it peaks along this peak intensity direction, but the levels are way higher. So it is not consistent with laboratory scale studies. And if you actually look at that skewness metric, so this tells you something about the waveforms or the shocks in the waveform on the y-axis, and this is the distance away from the jet along the peak intensity direction, then you see that the trends between the orange, the red, and the gray are very different. If you have a laboratory cold jet, a laboratory hot jet, or a full-scale jet. So this suggests that there is a specific kind of scaling mechanism going on for these shock type features. Now this led us to basically having to develop a small framework with which we can beforehand, before you actually do acoustic measurements, assess the expectancy of what we call cumulative nonlinear distortion. So do you expect this distortion to be significant or not? Now, we developed it as follows. We started with the wave equation here for a wave, in this case, a planar wave. And this on the left-hand side is just the change in the waveform with distance r, which is governed by two effects, namely this nonlinear term. This is really the term that causes the steepening of the wave. And then we also have this absorption term, which is a function of frequency, that tries to smooth out the shocks. And so it's really the relative weighting of these two terms that dictates whether you have any shocks developing or not. Now, just to review the absorption term is, of course, as we know, a function of frequency. So higher frequencies are subject to a much larger absorption than lower frequencies. This also depends on the humidity. But we have tabulated curves for this, so we know how to tackle that. And we define it in terms of the absorption length scale. So it's 1 over how many dB per meters of absorption you have. So it's an acoustic absorption length. Then for the shock, for the nonlinear distortion, the characteristic length scale that is being used is actually the distance that it takes for a harmonic wave to turn into an N-type wave with a shock, so where the derivative approaches infinity there. That is called the shock formation distance. And you can also analytically compute that for a planar wave in a lossless fluid. So if you have these two length scales, then people developed already in the 1950s and 60s by Gol'dberg, the Russians, and also Blackstock in the US, basically this ratio, so where you have the acoustic absorption length divided by the shock formation distance, which is called the Gol'dberg number. So it's kind of an acoustic Reynolds number that weighs the absorption versus the shock formation. And if this Gol'dberg number is much larger than 1, then the shock formation dominates, and you can anticipate shocks in your noise field. Whereas if it's smaller than 1, then the shocks will never really form. Absorption always dominates, and you can just compute your sound propagation with a linear model. So you do not expect this to be present in your noise field. Now, in the 1950s and 60s, it was only done for planar wave. When we started working on this, Mark Hamilton in the US also derived expressions for the Gol'dberg number for cylindrical and spherically spreading waves. Then you essentially have to bring in one more length scale, namely the radius of your source, which is the R0 relative to your shock formation distance. And you can see that then basically for a cylindrical wave, the effective Gol'dberg number, which we call here this capital gamma or capital lambda, it's the planar wave Gol'dberg number divided by this correction term. This is, I think, 2 pi. And then here we have essentially the radius of your source. So if you go to an infinite radius, you basically end up with the planar wave expression because it's just divided by 1. And you also have a similar expression for a spherical wave. So these can be analytically derived. And now, if you approximate any acoustic source in terms of a few variables, you can compute these effective Gol'dberg numbers. So the way it works is if you have an acoustic source, you have an intensity of the source. So for instance, the RMS pressure. You have a characteristic frequency. This is important for the absorption. And you have also a representative size of the source in case of a cylindrical or spherical source. Then you can compute these two expressions. And then when they are smaller than 1, you do not expect the distortion to be present. And larger than 1, you do expect. So after we derive this, basically it becomes a relatively back of the envelope calculation, except that you need to simplify your complicated jet noise source to a amplitude, a frequency, and a characteristic radius. So the way we do that for supersonic jet noise is as follows. This is the, again, the acoustic intensity with, basically, if you look along the peak intensity path, that's really the location where you expect nonlinear distortion to be most pronounced. You can look at how the sound intensity decays. So this is the pressure, the sound intensity, versus the distance here along that peak intensity path. So in the region far away from the jet, it follows spherical spreading, which you expect. It just decays as 1 over r. And then very close to the jet, it transitions to a cylindrical spreading, which you also expect because close to the source, the jet looks like a cylinder. So you can compute basically a Gol'dberg number based on the amplitude here and the spherical radius around the jet at about, in this case, 19 jet diameters, so an imaginary sphere. And you can also compute the cylindrical Gol'dberg number with the amplitude here, which is basically the jet noise source amplitude. And as a radius of the cylinder, you take the shear layer at that downstream position. So then we can just, based on any jet noise problem for supersonic jets, where this peak intensity is very well defined, compute the Gol'dberg number. So let me actually go to this slide then. So what we do here, we have this phase map, where on the x-axis we have the cylindrical Gol'dberg number, which for any jet is basically computed from the amplitude at this location and our cylindrical analytical solution for that number. And then the spherical one, which is on this axis, is computed from the amplitude here and also the spherical radius R1. And now your data points can be in these various regimes, these 4 quadrants, namely if for a certain jet, both the cylindrical and spherical Gol'dberg number are smaller than 1, so you're in quadrant 1, then you do not have any cumulative steepening in your domain. But then if you have, for instance, the cylindrical one, which is larger than 1, so that can mean that here in the cylindrical spreading regime, you have nonlinear distortion. But then if the spherical one is smaller than 1, the amplitude has already decayed so much that the nonlinear distortion is not really sustained any further to the far field. And therefore, this number is smaller than 1. And it actually turns out that the laboratory scale studies, so this red and orange data point, are in this regime. So therefore, for the laboratory scale studies, if you actually go to the far field of the jet, you do not really have nonlinear distortion happening at those locations because it only happened relatively close to the jet noise source. But then the data point for a full-scale jet is actually in quadrant 3, where even the spherical Gol'dberg number is much larger than 1, on the order of 100. And therefore, this explains or also shows that the full-scale jet noise data typically have this stronger shock-type features in their acoustic field. Now, why is that? Actually, the primary reason why the full-scale jet noise studies have these more pronounced nonlinear features is because at the end, the absorption is much lower because full-scale jets have a lower frequency, because typically they scale is a constant Struhal number, and a lower frequency for a full-scale jet, it peaks at about 400 hertz. The absorption is more than an order of magnitude lower than for full-scale laboratory scale jets, where with the smaller jet diameter, the frequency of the noise goes up, so you have way more absorption, not only per meter, but also per jet diameter of travel distance. So even though you geometrically scale your jet and maybe your measurement location, this doesn't scale in a geometric fashion. So what we now kind of emphasize is that if you look at these nonlinear features in laboratory scale environments, you should not only focus on aerodynamic similarity, which as aerodynamicists, we always focus on the same Reynolds number, or at least in a similar regime, say Mach number and temperature ratio to get, for instance, certain shock noise correct. But you should also take into account this acoustic similarity by taking into account this Gol'dberg number, with which you can actually explain, at least qualitatively, that in a full-scale jet noise field, you have way more intense skewness of the derivative of your waveform, so more intense shock waves than in a laboratory scale case. And because this is such important temporal characteristic to look at for the perception of jet noise, we should really rethink how to study this in a laboratory scale scenario, because you can actually not get acoustic similarity if you just follow aerodynamic similarity and geometric similarity. So, for instance, one way would be, of course, that you change the ambient medium. Then you can play around with the absorption and the shock formation distance. But this seems at least quite impractical in, for instance, an anechoic chamber. So that's the point I wanted to make for this jet noise topic, and that actually brings me to the end of the talk. So hopefully this has been followable by you, even though the internet may have been choppy, and I'm happy to answer any questions.